one more minute and then we will get started. Any questions so far before we get into the fundamental topics and then we will get into more applied. Any thoughts or comments or questions or all right, well, if not, let us get started. So, talking about second law of thermodynamics, there are as I mentioned, second law of thermodynamics creates a class system, right, for energy, that not all energies are created equal. So that lends to the concept of availability or the amount of work that you can extract out of a system, right. And so this availability comes in two forms. One is the Gibbs free energy and the other one is the Helmholtz free energy. I notice I have a typo here actually, or no, I think it's fine. So any idea what's the difference between Gibbs free energy and the Helmholtz free energy? When do you use Gibbs free energy and when do you use Helmholtz free energy? Do you all agree with that? So you are saying a closed system versus an open system, and how about a constant pressure system versus a constant volume system? Okay, I recommend that you all go back and review the free energy part and we will discuss it tomorrow once again. Okay. So, but in general, this is the definition. Okay, one is based on enthalpy and the other one is based on internal energy. So that itself should give you a hint of which one is for constant pressure and which one is for constant volume. Okay. So and the reason I am saying going through this is because when we derive the Young-Laplace equation, we will be using the concept of availability. Okay. Now we will also use a Clausius-Clapeyron equation, and basically this is the form of the Clausius-Clapeyron equation that tells you how the pressure and temperature, how they are related when there is a phase change. Okay. So you can derive this equation, it is very simple, I will not spend too much time on that. So now let us get into the concept of heat transfer. So what is heat transfer? Well, heat transfer is energy in transit due to a temperature difference. Any energy change that occurs or exchange that occurs because of temperature differences is called heat. And so what is thermal energy? Well, thermal energy is actually it's an energy that's associated with the translation, rotation, vibration and electronic states of the atoms and molecules that comprise a given matter in a particular system, and it represents the cumulative effect of microscopic activities and is directly linked to the temperature of that matter. Okay. So there are three modes of heat transfer, as we know. There is conduction, there is convection and there is radiation. And conduction typically for a good number of materials, your heat transfer or heat flux is proportional to the temperature gradient. It is not always true, but for certain classes of materials where you do not have heat generation, you could write your heat flux in this particular form. Okay. Now our focus will be more on the convection heat transfer in this particular Gyan course, and in convection the heat transfer that is associated with the bulk motion of a particular fluid is more on the convective heat transfer side, and typically the shortcut, the easy way to represent the heat transfer here is to use Newton's law of cooling, where your heat transfer is proportional to the temperature drop. Now when we teach this particular equation, this is valid for a macroscopic system. Okay. When we get to the nanoscale heat transfer, particularly when you go to the interface between a solid and a liquid, we will see that this can actually get violated, because sometimes you do end up with a thermal diode on the surface, as I mentioned earlier. Okay. And so when you have a thermal diode, this Newton's law of cooling needs to be modified, because in this particular case whether you have a hot surface or a cold surface, it does not matter, as long as your temperature drop is the same, your heat flux will be the same, right. But that particular modality may not always be valid, all right. So, we will revisit this equation a little later. And then of course, you also have heat transfer by radiation, and so when it comes to radiation heat transfer, the bodies need not be in contact. There could be a space in between the two objects, and they could still be exchanging heat energy, thermal energy essentially. And typically we use Kirchhoff's law, which says that when bodies are in thermal equilibrium, your absorptivity is equal to your emissivity, and if that is true, then you can write down the equation that is at the bottom of that slide. I am going through a little fast for this particular slides, because it is just I am trying to get you all up to date on the basics of heat transfer. And then you can represent the radiation heat transfer by a equivalent radiation heat transfer coefficient. So and then comes the concept of the thermal resistance. So in case of a convective heat transfer, you can represent the thermal resistance by the inverse of the heat transfer coefficient, and when it comes to conduction heat transfer, your the conduction resistance is proportional to the ratio of the thickness of the material divided by the conductivity of the material. Now the other concept is that of a extended surface. When we deal with the extended surface or a fin, we assume that there is no temperature drop in the transverse direction, the temperature drop is only in the radial direction. We neglect any temperature drop in the transverse direction of the extended surface. Okay, if you make that assumption, you get what is known as the fin equation, the differential equation, and you can solve it for different types of boundary condition. So you can have a convection tip boundary condition, you can have a adiabatic tip boundary condition, you can have a fixed temperature tip, and you can have an infinite fin. Okay. So and then how do you determine if a particular fin is worth the money that you invested in making it? So there are two ways of looking at it. One is what is known as fin efficiency, which is the actual heat transfer divided by the maximum possible heat transfer, and then the other one is the fin effectiveness. Okay, those are the definitions that you have over here. Now coming more into transient heat transfer, the easiest model you can think of is that of a lumped capacitance model, where you neglect the temperature drop within the solid object, and you treat the whole object to be at one fixed temperature, and that whole temperature varies with time. Now in order for you to make this approximation, you are assuming that the temperature drop within the solid is very small compared to the temperature drop from the solid to the fluid, or in other words, there is this non-dimensional number, Bio number, which represents the conduction resistance to the convection resistance, the ratio of those two resistances, and typically your convection resistance is much higher than the conduction resistance. And now you can see there is an equation that is marked in a yellow box. Okay, pay close attention to this equation, because we will be coming back to it when we look at carbon nanotubes and the heat transfer from a carbon nanotube into a fluid. Okay. So what you see is your the temperature at any instant of time divided by the temperature difference when you started the transient heat transfer. If you take that ratio is proportional to a time constant, okay, e to the power of minus t by tau, and tau is the time constant. So and that time constant you can break it up into two parts. There is a conduction resistance part and there is a capacitance part. So this becomes your RC circuit, right? In an electronic circuit you have RC circuit, right? So this is the equivalent of a RC circuit. So you have a decay or a rise in current as a function of time in an electric circuit. Similarly, if you look at the heat transfer or the temperature as a function of time, it goes through a exponential shape. Now if you look at the time constant, if I do it on a per unit area basis, then it is a function of the product of the R, the resistance and the capacitance, the thermal resistance and the capacitance, and then the surface area of this particular object, right, that is in the denominator. So, this is the equation we will come back and use once again, okay, when we do molecular simulations, all right. So, and then there is a concept of a semi infinite solid. So, when you are operating at very small time constant or at very small times, you know, the penetration depth of your, so if I expose the surface of an object to a sudden change in temperature or a sudden change in heat transfer, for that effect to diffuse into deep into the body of the object, it takes some amount of time, okay. So, if you are operating at very small times, when it has not penetrated deep into the body, then your temperature fluctuations are confined to a very thin skin very close to the surface of the object, right. And so, if that is the case at very small times, you can neglect the curvature of the body, okay. So, it does not matter whether it is a plane wall or a cylinder or a sphere, okay. So, what I mean by that is, if you look at the graph over here, there is this non-dimensional heat transfer Q star plotted against a non-dimensional time or Fourier number, okay. And so, the graph that you see on the left hand side is for an interior object, which means you take a sphere and you impose heat on the sphere, okay. So, the heat is going into the interior of the object, or you could have a situation where you have a pipe embedded in ground and the pipe could be taking a hot fluid all of a sudden, and so now the heat is radiating out into the object instead of radiating in, okay, or traveling out instead of traveling in. So, the one on the right is for I am sorry, yeah, I take it back. So, the one on the right is for a heat flux imposed on the surface, and the one on the left is a temperature boundary condition imposed on the surface. And you can see that there is a straight line that is marked as semi infinite solid, right. That is a response that you get from the semi infinite solid equation. Now, if it is an external object, that goes above the semi infinite solid line, the response, and if it is an internal object, then it goes below the semi infinite solid line. And what you see is, when your Fourier number is less than 0.01, ideally less than 0.001, there is a very small departure compared to your real between your real equation and a semi infinite equation, or in other words, if you have a particular transient problem where the Fourier number is less than 0.001, you can treat it as a semi infinite solid and you do not have to worry about the curvature of that object. So, it does not matter whether it is a plane wall, it is a solid sphere or a solid cylinder, the semi infinite equation, which is a much simpler equation, will give you the solution to pretty good accuracy, okay. So, keep this in mind, because we will be revisiting this also a little down the road. And then coming to free convection, and when you have a hot plate facing up or a cold plate facing down, if you are in a situation like this, instead of just like in a flow we talk about Reynolds number, in a situation like this we talk about Rayleigh number, okay. And if you look at the structure of the Rayleigh number, there is gravity, there is expansion, volumetric expansion coefficient, you have your temperature drop, and then it goes as length cube divided by thermal diffusivity and viscous diffusivity, right. And typically, if it is a vertical plate, if your Rayleigh number exceeds 10 to the power 9, then you are in the transition regime or turbulent flow, okay. Below that Rayleigh number, you are in laminar natural convection. Now, if it is a flat horizontal plate, let us say a hot plate facing up, then you see the two Nusselt number equations at the bottom. Do you have the pointer? Excuse me. Okay. So, so what you see is the last two equations at the bottom. Thank you very much. So, what you see is the last two equations in the bottom. When your Rayleigh number is less than 10 to the power 7, you are in the laminar flow regime, and when you are in the when your Rayleigh number is more than 10 to the power 7, you are in the turbulent flow regime, okay. In the first case, it goes as Rayleigh number to the power 1/4, and in the second case, it goes as Rayleigh number to the power 1/3. So, today when we do the tutorial, we have a 1 hour tutorial, we will come back and revisit this, and there is this question, what is the dependence of the heat transfer coefficient, the average heat transfer coefficient on L when you are in the turbulent flow regime? Can you take a guess? Okay, so think about it, we will come back to it when we are in the tutorial session. Okay. And then we are going to also look at heat transfer from cylindrical heaters like a wire or a pipe, and spherical heaters. So if you look at the natural convection equation, this is the natural convection equation when you have a circular sphere, and I apologize, for some reason a part of the picture is not showing up over here. Let me see if I go out of presentation mode, if it will show up. For some reason it does not show the boundary layer. Can you all see the boundary layer? Probably not, right? So on my screen here I can see the boundary layer, but for some reason the projection system is not showing it. But any case, so one interesting thing about heat transfer over a curved object like a cylinder or a sphere is the last 30%. If you look at the Nusselt number as a function of angle, with theta starting here and going up all the way over here, it decreases very sharply for the last 30% of the surface. In other words, I can treat the surface as being insulated starting from here, okay, and my answer will not change by more than 5%. Or in other words, about after about 70 degrees, after you exceed an angle of 70 degrees, the rest of the surface is virtually insulated, okay, and so that affects your average Nusselt number calculation. So you can see it is almost virtually flat, and then it drops very sharply. So you can think of it as a sort of a step function. Okay, so when we are dealing with film boiling, we will come back and revisit this same structure. You will see in film boiling also you get a very similar formulation. Okay. So now the basics of pool boiling. So typically when you start pool boiling, you start the heater by heating it up first, and you get natural convection on the heater before the first set of bubbles appear. And so let us look at an example of a typical electronic chip being cooled because of boiling of a refrigerant on top of the electronic chip, right. So if you use a saturated fluorocarbon, for example things like PF5060 or FC72, their boiling point is about 57 degrees Celsius, and if you substitute the properties for this fluid, you get a critical heat flux which is about 60 to 70,000 watts per meter square. Okay. Now as a thermal design engineer, you do not want to operate at the maximum heat flux point, you probably want to be a little below. So let us say about 10% below your maximum point. So you probably want to operate at 0.9 of the Q max. Okay. And so in a situation like this, I can have pool boiling, I can have a forced convection boiling, I can have saturated boiling where the refrigerant is at homogeneously at 57 degrees Celsius, or I can have subcooled boiling where the refrigerant is at a temperature lower than the boiling point. Okay. Now if I plot the heat flux as a function of this delta T excess, which is the heater temperature minus the boiling point or the saturation temperature, that is what is plotted on the x axis, and this is plotted on the y axis. What you will see is initially you are in the natural convection regime, and then the heat transfer goes up where the heat flux is almost here your Q is sort of proportional to delta T. Okay. It is almost linear in delta T, but when you get to once the bubbles start forming and it is in a pretty stable mode of boiling, then your heat transfer is actually proportional to delta T cubed, okay, until it hits the maximum heat flux point. And then if you exceed the temperature more than the maximum heat flux point, then things go a little uncertain at this point, or what you have is the boiling instability. And then at that point, depending on the history of your heating or the amount of heat flux that you are supplying to the system, your curve can change. But if you are in a constant heat flux mode, any marginal increase in heat transfer above this critical heat flux point, you actually end up in the film boiling curve. Okay. And in the film boiling curve, again it is pretty repeatable, I can go up and down this curve as many times as I want, as long as I do not hit the minimum heat flux point here or the Leidenfrost point. It is a fairly repeatable experimental protocol. Okay. But in between, this whole thing becomes a little uncertain, or what is known as a transition boiling. Now, if you notice, they have plotted it with dotted lines here. Why do you think they have plotted it with dotted lines? Any idea? Go ahead.
Practically unachievable. When we cross that max line, max point, sudden heating occurs. So when experiments were done initially by Nukiyama, he was able to achieve those black
the solid lines,
the black arrow lines,
right?
Like up to the near burnout point and back, but not that zone ever.
Right.
Practically, so that's
okay. So in other words, this is a zone where you cannot have steady boiling in a steady state. It is a very unstable situation. It is very difficult to control, and depending on the history of your imposed boundary condition, whether it is temperature or heat flux, you can end up in different parts of the curve. So in thermodynamics, when we plot something with a solid line, we mean it is a repeatable process or a reversible process. And when we plot that is the convention in thermodynamics, when we plot something with a dotted line, it means it is irreversible or it is not possible to repeat it. Okay. So in this zone, it becomes highly unrepeatable. Okay. Now, if you look at the boiling structure at different parts of the boiling curve, well, you start with a natural convection initially, and then at some point at about 5 degrees above your boiling point, or your delta T being about 5, your first set of bubbles start appearing, or what is known as your onset of nucleate boiling. And typically in this mode, the bubbles start forming on the surface, but only a few of them depart from the surface, rest of them just stay on the surface and stay stuck there. Okay. And then as you keep increasing the heat transfer, now your bubbles start departing from the surface. They form, they grow, and then they depart. Okay. And then when you get close to the maximum heat flux point, the rate at which the bubbles form is actually almost marginally bigger than the rate at which the bubbles depart by terminal velocity in the fluid. Okay. And so you have a vertical merger of the bubbles in the vertical direction, and you end up with columns. And in certain situations, the columns start oscillating and they join with each other, and they trap superheated liquid in between them, and they form a mushroom shaped bubble. Okay. So you have a mushroom shape because the two columns joined up, and then there was a liquid that was trapped in between the two columns, and that takes a sort of a mushroom shape. And so this superheated mushroom shaped column has a very high surface area, and that actually starts feeding steam or your vapor at a very high rate into this mushroom bubble essentially. Okay. And then if you any marginal increase in above the critical heat flux point, now the bubbles start merging in the horizontal direction, and they sort of start creating a vapor blanket. Okay. And in this situation, now you have a very weird issue, which is if you increase the energy input into your system, that blanket grows, and if that blanket grows, it is trying to insulate the heater. Okay. And so you are trying to increase the heat flux, but actually your heat flux is decreasing. Okay. Or the other way around, your temperature is decreasing and the heat flux is going up. Okay. So you have a negative curve in your system where increasing the temperature actually results in a decrease in the heat transfer. Okay. Or the other way around, any sort of if you are trying to increase the heat transfer, your temperature actually drops. Okay. And so you operate in the transition regime, which is very difficult to replicate, and finally you end up with a film boiling regime where you have a blanket of this vapor. Okay. Now this blanket of this vapor is not stable. Okay. So there is ripples that form at the interface between the vapor and the liquid, and you form a traveling wave. Okay. So you can have a traveling wave or you can have a standing wave. Okay. You can have two different configurations, but if you look at the shape of this film, at some points you have a lower thickness of the vapor bubble, and at other points you have higher thickness of the vapor. okay. And so wherever you have a lower thickness of the vapor, you get a higher heat transfer, and wherever you have a higher thickness of the vapor, you get a lower heat transfer, okay. And so because there is a variation in your heat transfer, the temperature on the surface of the heater changes, okay. Now the weird thing is, when the temperature of the surface temperature of this heater changes, you cannot measure it, because typically your thermocouples are about a couple of millimeters below the surface, and so all that temperature oscillations that are occurring right on the surface of the heater, they damp down by the time it reaches the thermocouple, number one. Number two, those temperature variations, that fluctuations, are actually of smaller size than the size of your typical thermocouple. Your typical thermocouple is of the order of a millimeter, right, versus your vapor bubble that forms in a refrigerant, for example, is of the order of about 600 microns or 0.6 millimeter, okay. So these temperature fluctuations that you are seeing is occurring of the range of about 300 to 500 microns, about 0.3 to 0.5 millimeter. So there is no way a big 1 millimeter thermocouple will able to sense it, okay. So that's one part, but the interesting thing is that temperature fluctuations that occur on the surface, even though it's in a steady state boiling regime, the temperature actually fluctuates pretty widely, okay. So to illustrate that, that's the movie I was trying to show you at the very beginning. Actually, unfortunately I had to break up my slides because the computer was freezing. So let me pull up that simulation once again, the simulation result once again. So what you see is a CFD simulation. At the point of the minimum vapor film thickness, you get a peak in the heat transfer, and so therefore it causes a local cooling. That blue dot is your cold spot, okay. And when the bubble departs, your cold spot is in the center, and when the bubble forms initially, your cold spot sort of moves from the outer periphery towards the inner portion of the bubble. So this is how the temperature fluctuates under the bubble. And typically, if you look at the bubble departure cycle, and we will get into those calculations a little later, your typical frequency of bubble departure in film boiling is of the order of 10 hertz, which means you are departing one bubble every 100 millisecond, okay. And we will get into the details of film boiling a little later, and typically what you have is the bubbles depart alternately from neighboring sites, okay. So for 50 millisecond, a bubble departs from one side here, and after it departs, the next bubble forms a certain distance away, and that forms for 50 milliseconds, okay. So for the first 50 milliseconds, your temperature transients are almost not there, and for the next 50 milliseconds of the total 100 millisecond departure cycle, you see this temperature fluctuation occurring, which means your temperature fluctuation should have a natural frequency of the order of 20 hertz, isn't it? So the bubble departure frequency is 10 hertz, but your temperature fluctuation will be of the order of 20 hertz. So you expect the temperature fluctuation to be somewhere between 10 and 20. Does that make sense? Okay. And so what I have plotted here is the cycle time. This is about 50 milliseconds. The clock that you see over here is 50 milliseconds, okay. So any case, so what the computer model is telling you is that for film boiling, your typical temperature transients are somewhere between 10 and 20. Does that make sense, right? And then the second thing that it was telling us was this point at which you have the minimum vapor film thickness. The computer model was predicting it was of the order of about 15 microns, okay. Here the bubble is going to grow up to about, let's say, 500 to 700 microns, let's say, okay. So but so that vapor blanket that has formed, that thickness of that blanket is going anywhere between 10 microns all the way to 70 microns within a distance of about 500 microns, Okay. So, that is a big variation in the thickness of your blanket if you think about it. If you treat the vapor layer as a blanket, that blanket has a wave on it, and that wave actually is going through a big change within a very short distance. Okay. So, anyway, so film boiling is a very interesting and complicated, complex phenomena, instability phenomena, and now a big question is, what do you think, is the vapor blanket always stable, or do you think it gets punched? What would you think? So, let us say I am at pretty high up in this graph over here. Will this blanket collapse? Okay. The question is, what do you mean by surface? You mean surface roughness, right? But surface roughness is a double edged sword. The conventional measurements of surface roughness only measure the depth of the roughness. They do not measure the gradient of the roughness. You see what I am saying? So, I could have a lot of small sawtooths, or I could have a gradual rolling hill. Will both of them have the same roughness? So, when you measure roughness, there is a roughness parameter, right, that measures the standard deviation of this profile, right. But in any case, let us assume that you have a plane surface, fairly non rough, fairly smooth. Let us say I have a silicon wafer which is atomically smooth, right. Your typical silicon wafers are single crystals, and they are polished to almost single lattice constant surface roughness. It is almost flat, plain and flat. So, in a surface like that, if I am operating pretty high up here, do you think that vapor blanket is stable? Well, when I am over here at the minimum heat flux point, of course, they collapse, and then you get into nucleate boiling once again, right, or you get into transition boiling, where a part of the heater is in nucleate boiling and then a part of the heater is in film boiling. But when you are in steady film boiling, you expect that vapor blanket to be fairly stable. But there were experiments done in the late 60s that showed that even in a stable vapor blanket mode, there is periodic contact of the liquid that hits the surface of the heater, and then by like a rocket recoil, the vapor pushes it back. Okay. So, what they did was they put some electrolyte in this solution. So, now it becomes electrically conducting, and then they put an electrode into the solution, and they put an electrode on the heater or the metal, and if there is a contact between the liquid, it should show up in an oscilloscope, and they showed that it does show up. But if you chill the liquid, if you subcool it, those contacts go away. So, in saturated film boiling, even if you are pretty high up over here, there is periodic liquid solid contacts that occur, and your conventional film boiling models do not really account for that phenomena. Okay. So, the conventional models for film boiling, Berenson's model for example, works very well when it comes to subcooled boiling. Okay. But when it comes to saturated boiling, the Berenson's model actually does not account for this phenomena, the periodic liquid solid contacts. Okay. So, not a lot of textbooks actually talk about this phenomena, but there are evidences in the literature where the vapor film even in stable film boiling collapses at localized areas. Okay. Yeah, water is not conducting until you put some kind of salt in it, right. If you have pure water does not conduct. Only if there is some kind of electrolyte or impurities, then it starts conducting. Okay. And so, those periodic liquid solid contacts experiments were done with water, and they put some electrolytes in there, so it becomes electrically conducting. Okay. So, if I talk about the boiling curve, in nucleate boiling you have isolated vapor bubbles, you have jets and columns. So, this is a very good picture of when you go very close to critical heat flux on a wire, and you can see sort of the vapor columns forming on the wire. Okay. And then when you get into film boiling, this one shows that your vapor bubbles are departing at fixed periodicities. Okay. And the distance between two vapor bubbles, you can predict it based on instability theory. Okay. There is something known as Taylor instability wavelength, which we are going to talk about tomorrow. Okay. And so, what people find is that this periodicity between these vapor bubbles that are departing alternately from one location and the other, you can predict it fairly well if you know the Taylor instability wavelength. Okay. Let us see. And then for transition boiling, you can do two different ways. You can do a heat flux controlled experiment, or you can do a temperature controlled experiment, but in either case it is very difficult to repeat the experiment. And when it comes to pool boiling, the nucleate boiling part of the curve is given by Rosenhaus equation, and here your heat transfer is proportional to delta T cubed. Okay. Now, when it comes to the maximum heat flux, that's that's Zuber's correlation, and it's typically given by this equation over here. Okay. Now, whether you are looking at this equation or this equation, you will see that there is this term over here, that's a ratio of gravity times density difference divided by surface tension. Okay. If you calculate, if you do a dimensional analysis, this has the units of length or inverse of length. Okay. And so, this is what is known as the length scale in boiling. We are going to look at it tomorrow once again. Okay. This sigma divided by G delta rho has the length scale, is typically your length scale. So, remember in the first half I talked about this pendulum, and you shrink the size of the pendulum, the frequency goes up. So, this length scale also has a influence on the frequency of bubble departure. Okay. If I use two different fluids which give you two different length scales, boiling length scales, you will see that their frequencies of at which the bubbles depart, whether it is in nucleate boiling or film boiling, okay, whether it is at critical heat flux or in film boiling, they will be proportional to that length scale L naught. Okay. We will look at it tomorrow. And then if you get into film boiling, you are typically using Berenson's correlation, which is the correlation given over here, and once again you see that the heat transfer coefficient is inversely proportional to the delta T to the power of 1/4, which means your heat transfer coefficient is almost constant, because your temperature drop has to go up by a factor of 10,000 in order for your heat transfer coefficient to go up by a factor of 10, or the other way around, your temperature drop has to go up by a factor of 16 in order for your heat transfer coefficient to double. Okay, which means if you plot your heat transfer coefficient as a function of your delta T, it is almost a flat line. Okay. And it becomes geometry invariant for certain diameters of cylinder and sphere. So, these correlations that you see over here, okay, are for large cylinders. Okay. So, when you do the boiling experiment on a thin wire versus a big pipe, your heat transfer coefficients will not be the same. Okay. We are going to look at it a little later. Okay. So, the size of the heater affects your heat transfer. So, when you write your Q equal to H delta T, right, that assumes that your heat transfer is independent of the size of the heater, is not it? Right, because they are saying the heat flux is independent of the area, but when it comes to boiling, the size of the heater affects your heat flux. Okay, we are going to look at it. So, when you design a boiling experiment, you have to pay careful attention to what is the size of the heater that you are using, and this is a very common mistake that is out there in the literature, people make very often. Okay. In other words, if I have a small heater, okay, I will actually get a higher heat transfer or heat flux, everything else being the same. Okay. Does that make sense? Okay. And so, all these correlations that you see over here does not have the effect of the area explicitly in them, but implicitly the size and configuration of your heater will affect your heat flux. Okay. And so, in other words, I will need a correction factor to my heat transfer coefficient if I have a smaller heater compared to a large heater. So, when is a heater small and when is a heater large? Okay. We need to come up with a criteria for that also, is not it? And so, we will discuss that as well. Okay. Does that make sense? How many of you knew this phenomena, that the size of the heater affects the heat flux? Any of you knew about it? No? Okay. All right. So, anyways, and so when it comes to film boiling, radiation also becomes an important parameter, because in any natural convection system not involving boiling, typically if you look at the total heat transfer, about half of it comes from natural convection and half of it comes from radiation. So, in a natural convection environment, you cannot neglect the contribution of radiation, they are almost of the same order. Okay. When it comes to nucleate boiling, you can neglect radiation, because your boiling heat transfer is so high and it typically occurs for very small delta T's. But when you are in film boiling, your delta T's are pretty big, of the order of 50 to 100 degrees Celsius, okay, and your heat transfer coefficient H is also very small. So, in that situation, now you cannot neglect radiation. So, there are correlations people have come up with, which accounts for the radiation heat transfer coefficient as well. Okay. Condensation, let me skip it, I will come back to this later on when we get into the condensation lectures, in the interest of time, because we started a little late today. So, I have to make up for it. We will come back to these lecture slides 2 days from now. So, let us see. The next is I wanted to get into the derivation of the Young-Laplace equation, and then talk about nano bubbles. Okay. So, the Young-Laplace equation is deceptively very simple. Okay. What this Laplace equation tells is, if I have two phases, I have, oh my goodness, okay, we have a problem, right. Okay, I think I have to draw it. Okay, it is not showing up on the PowerPoints. Good. Okay. So, let us say I have a sort of a spherical geometry, and I am looking at a patch of an area. Can you all see it? Okay. And so, if I look at this particular patch, this semi spherical patch, I will see that it will have two radii of curvature. Okay. So, when I look at this surface, it has a radius of curvature, let us say R1. Okay. versus when I look at this surface over here, it will have a different radii of curvature R2. So, what the Young-Laplace equation says is, if I have phase 1 on this side and phase 2 on this side, okay, the difference in pressure between the two, delta P, is equal to this term called surface tension times 1 by R1 plus 1 by R2. Okay. And if it is a perfect sphere, then both your R1 and R2 are same. So, you end up with, so when your R1 is equal to R2, you end up with delta P equal to 2 sigma by R. Okay. But the question is, where did this equation come from, and what are the assumptions that are built into this equation, okay, for you know for deriving this equation. Okay. So, in order for us to get back to this equation, we will have to start with what is known as Gibbs free energy. Okay. So, now let us start with a very simple situation. So, let us think there is a closed system. Okay. So, let us say you have a closed system and it is adiabatic, which means there is no heat transfer. Okay. And in this system, I have two different phases. I have a fluid of phase 1 and the same fluid of phase 2, maybe a liquid and a vapor. Okay. And so, because this is a closed adiabatic system, the energy of the system is just the internal energy, right, just the kinetic energy of the molecules. So, the internal energy, whether I am in phase 1 or phase 2, is a function of two quantities. Okay. One is entropy S and the other is the number of molecules. More molecules I have, the more energy I have in the system, total internal energy I have. Now, what do I mean by S? Entropy, we are going to define it. Okay. So, if let us say a few of the molecules from phase 2 move into phase 1, okay, then the number of molecules in phase 1 has gone up and the number of molecules in phase 2 has gone down, right. So, U1 will be equal to and similarly my U2 will be equal to the number of molecules and the entropy of the system, right. So, if I have any change in energy U du, that will be equal to del U del S with n being constant times ds, right, and then I will have del U del n times change in n. Okay. So, this change, this del U with S, I call it as this property temperature. Okay. And so, this is a function of n and shape, actually the shape of this interface. Okay. And so, here your S is constant and shape is constant. Okay. And then the change in internal energy with the number of molecules, I call it mu, and this is nothing but the chemical potential. Can you all see my writing at the back? Okay. So, the n of the system is equal to n 1 plus n 2 and that is fixed. So, which means my d n system is equal to 0 and that is equal to d n 1 plus d n 2. You all with me on this? Okay. And similarly, my since there is no heat transfer, the S of the system is equal to the entropy in phase 1 plus entropy in phase 2. So, if I do a ds system, that should be equal to 0 because there is no heat transfer, and so that should be equal to ds 1 plus ds 2. You all with me? And so, if I write down my equation, my du is equal to TdS plus mu dn. Right. So, if I write it out, okay. So, therefore, my du system will be equal to T 1 ds 1 plus mu 1 dn 1 and let us see plus T 2 ds 2 plus mu 2 dn 2 and that should be equal to 0. There is no energy transfer to the system. So, the internal energy, the total internal energy should not change, right. But I know that my ds 1 is equal to minus ds 2 and then my dn 1 is equal to minus dn 2, right. So, what I will end up with then is T 1 minus T 2 times ds 1 plus mu 1 minus mu 2 times dn 1 is equal to 0. Now, S and N are independent of each other, right. So, in order for this equation to be valid, each of these coefficients have to be 0. Does that make sense? Okay. So, if the shape of the interface does not change, okay. So, for a sharp so if you have a sharp interface that does not change shape, the temperature has to be isothermal and the two chemical potentials also have to be equal. Okay, that's the simplest case that we have considered. Are you all with me here? Okay. Now, let us look at a system where the shape is not sharp. So, in that interface I have molecules that are neither in phase 1 nor in phase 2, okay, but that is a very thin interface with almost negligible volume, okay, and the shape can change, the shape is not constant anymore. In other words, the area of that interface can change. Okay. So, I am making an assumption. So, pay close attention, interface is not sharp. Okay, that is the first assumption. The second assumption is interface is deformable. Okay. Now, my internal energy is a function of 3 variables: the entropy, the number of molecules, and the surface area, okay, where my A is the area. So, now I am going to come up with a factor which is del u del A for S and N being constant, and I am going to call it sigma, which is surface tension. Okay. So, that is the formal definition of sigma, the surface tension. And so, if I look at the Helmholtz free energy, U minus Ts, that is the work that I can extract out of the system, that is the definition, right. So, if I write down the change in, so let us say the surface deforms, or some molecules from phase 1 go into phase 2. Okay. So, the other thing I forgot to mention. So, now if I look at my system, I have phase 1, I have fluid 1, I have fluid 2, and in between I have this very thin region, the interfacial region, where the volume is negligible. So, the internal energy here I call it as U star, and that is a function of S, N and A. It is not a function of volume, it is a function of the surface area, okay, and I denote it by star. All right. So, my dF will be equal to du let us see, minus TdS minus S dt, okay, plus mu dN actually I am sorry, let me take a step back, sorry about that. So, if I look at the phase 1 and 2, I have my U being a function of S, N and V. So, that is my U1. Similarly, I will have a U2 which is a function of S2, N2 and V2, and then I will have a U star which is S star, N star and V star. So, if I write down my du1, my du1 is going to be TdS1 plus mu dN1 plus PdV1, where this parameter P is del U del V, okay, at constant S and N. So, similarly, I will write a du2 which will be equal to T2 ds2 plus mu 2 dN2 plus P2 dV2, and then I will write a du star which will be equal to T star I am sorry, I wrote it in the wrong way. Let us do it fresh. So, if I do a du1, I will get T ds1 plus mu dn1 plus P dv1 . Similarly, if I do a du2, I will get a T2 ds2 plus mu 2 dn2 plus P2 dv2, and similarly if I do a du star, I will get a T star ds star plus mu star dn star plus sigma times dA. Okay. So, now if I want to see how much is the work that I can extract out of the system, I go to Helmholtz free energy and I define it as U minus Ts. Okay. So, if I look at the change in the Helmholtz free energy because of the deformation of the interface, if I substitute these equations, I will end up with okay. Now, implicit in this derivation of this equation, I am making an assumption, okay, and that assumption is that the radius of curvature of the interface region is much bigger than the thickness of that interface. Okay. So, keep this in mind, because when we discuss nano bubbles, this one will become an issue. Okay. Now, since the volume of the system is constant, so your dV is equal to dV1 plus dV2, and that should be equal to 0. Okay. Similarly, your dN system is equal to dN1 plus dN2 plus dN star, and that should be equal to 0. And if I assume that this whole thing is isothermal, okay, so that is the other assumption I am making, that it is a isothermal system. So, your dt is equal to 0. Okay. So, if I make this assumption, what I end up with is P1 minus P2 is equal to sigma times dA divided by dV1. You all with me on this? Okay, so that is the equation I end up with. Now, the question is, what is dA divided by dV1? Okay, we got to figure this one out. So, to figure this dA by dV, let us look at the interface. Okay. So, let us say my interface, I take a small area dA, okay, and let us say because it is getting deformed, this interface has moved by a distance dy, okay, and now it is at a different location. And let us say it had a length L1 along one side and a distance L2 on the other side, and now that it has moved, this L1 has become L1 plus dL1 and this L2 has become L2 plus dL2. Okay. And to begin with, this guy had a radius of curvature R1, another radius of curvature R2, right. So, its initial area was L1 times L2, right, but now that it has moved, so dA is L1 times dL2 plus L2 times dL1, okay, and the change in volume of phase 1 is L1 times L2 times dy, right, the initial area times the distance it has swept. You all with me on this? So, now let us look at it from the top view. Okay. So, how does the top view look? Well, it was L1 with a radius of curvature R1, now it has moved so it has moved by a distance dy, and so if this one was L1, now it has become L1 plus dL1. Does that make sense? Similarly, if I look at it from the side, well, it was radius of curvature R2, it has moved by a distance dy, and this one was L2 and now it has become L2 plus dL2. You all with me on this? So, if I use the similarity principle, then my L1 by R1 should be equal to L1 plus dL1 divided by R1 plus dy, isn't it? Similarly, my L2 divided by R2 should be equal to L2 plus dL2 divided by R2 plus dy. Make sense? Now, the whole reason I am doing this is because I want to figure out this term dA by dV. How much does the area change per unit change in the volume of phase 1 or phase 2, right. So, anybody know this rule called the rule of componendo and dividendo? Well, it is a very simple rule. It says that if A by B is equal to C by D, that is equal to A plus C divided by B plus D. Very simple, isn't it? So, if I look at this equation, I have L1 by R1 is equal to L1 plus dL1 divided by R1 plus dy. So, A by B is equal to A plus C divided by B plus D. So, that should be equal to C by D, which is dL1 by dy. You all agree with me? Similarly, I can write my L2 by R2 should be equal to dL2 by dy. So, this implies that my dL1 is equal to L1 by R1 times dy, and this implies my dL2 is equal to L2 by R2 divided by di. You all with me? And what we say was my dA? My dA was equal to L1 dL2 plus L2 dL1, and my dV1 was equal to L1 L2 dy, right. So, if I substitute dA by dV1, I will end up with dL2 by dy times, let us see, times 1 by L2 plus dL1 by dy times 1 by L1, isn't it? So, I can substitute my dL2 to be equal to L2 by R2 times dy. So, I can write it as L2 by R2 times dy times 1 by L2 times dy plus L1 by R1 times dy divided by 1 by L1 times dy. So, what do I end up with? I end up with 1 by R1 plus 1 by R2. So, therefore, your P1 minus P2 is equal to sigma times dA divided by dV1, and that is equal to sigma times 1 by R1 plus 1 by R2. Okay. So, that is your Young-Laplace equation, but then the question is, what assumption did I make? So, let us recap what were the assumptions we made. Okay, interface is not sharp, interface is deformable, right, that was the first set of assumptions we made. The next assumption we made was the radius of curvature of the interface is much bigger than the thickness, okay. And then the final assumption we made was it is an isothermal system. All right. So, let us keep that in mind. Now, let us move back and look at the concept of nano bubbles. Okay. So, this is a very recent phenomena and there is a lot of controversy, and people still do not have a closure to these controversies. So, before we go there, let us look at a couple of other concepts. Okay. The next concept we have is that of a homogeneous nucleation. Okay. So, I guess it is 4 o'clock, we are supposed to start with our tutorial, but we will do a 30-minute tutorial. Let us finish this concept over here. Okay. And so, the concept of homogeneous nucleation is, if I have an infinite mass of water or some liquid, okay, and let us say I heat it up to a particular temperature, and when I heat it up to a particular temperature, spontaneously a vapor bubble forms in that mass of liquid. Okay. So, there is no solid surface present. Normally, when you have boiling, you have a solid surface on which you form a vapor bubble. Okay. But if you want to spontaneously form a vapor bubble, then you have homogeneous nucleation. It forms in the homogeneous medium, that it is a part of the molecules separate out and they form a vapor bubble. Okay. So, let us do the thermodynamic analysis for when a homogeneous nucleation can occur, under what set of conditions I will get homogeneous nucleation. Okay. So, actually let us go back to the drawing board. So, let us say I have a very large body of liquid or water, for example, and I heat it up at a particular pressure. I heat it up to a certain temperature, I do not know what the temperature is, but let us say I heat it up to a particular temperature, that it spontaneously forms a vapor bubble of radius r. Okay. So, let us say n is the total number of molecules in the system. and then we write small g as the Gibbs energy per molecule. Okay. And let us say NT is the total number of molecules. Okay. So, the number of molecules of vapor, let us call it as Ng. Okay. So, after the vapor bubble forms, then the remaining number of molecules that are liquid is N minus Ng, Nt minus Ng. You all with me on this? So, after the vapor bubble forms, this is the number of liquid molecules I have. So, if I write down my Gibbs free energy, okay, before the vapor molecule formed, my availability of the system was Nt times GL, okay, where GL is a Gibbs energy per molecule for liquid, okay, and then Gg is Gibbs energy per molecule for vapor. Okay. But now that the vapor bubble has formed, my current availability then will be equal to number of gas molecules times the Gibbs free of the gas molecules plus Nt minus Ng times GL, and because I have formed a extra interface between the liquid and the vapor, so it will be sigma times, if I assume it is a spherical bubble, then the area of that bubble is 4 pi r square. Right. And if I use the gas law, then my Ng will be equal to the volume of the bubble times the density of the gas, that is the total mass of that bubble, divided by the molecular weight, that gives me the number of moles, right, and that times the Avogadro number Na gives me the total number of molecules in that gas bubble. Does that make sense? Okay. So, if I substitute that, my A will be equal to 4/3 pi r cubed, which is the volume of the gas bubble, times the density divided by the molecular weight, times the Gibbs free energy plus well, since I have two Ngs over here, I can combine these two Ngs and I can write it as Gg minus GL plus Nt times GL plus 4 pi r square sigma. Okay, and I already said that my A prime is equal to Nt times GL. So, my delta A is my final availability minus initial availability, right. So, if I write it down, my final availability, the change in availability delta A then becomes equal to 4/3 pi r cubed times rho g by m times N A times G G minus G L plus 4 pi r square sigma. Okay, so, if you look at it, my delta A is some constant times r cubed plus some constant times r square, is not it. So, it has two components, one component it goes as r cubed and the other component goes as r square. One depends on the volume of the vapor bubble, the other depends on the surface area of the vapor bubble. There are two parts to the total availability of my system, right. Now, I want to find out what is the minimum radius at which my availability is maximized, because then my system will try to spontaneously go to that radius first, is not it, whatever maximizes my change in availability. Okay. So, I am interested in finding out this d delta A by dr equal to 0. Okay. And the condition in which it occurs, that radius is my critical radius and I call it r equal to r c. When r is equal to r c, my availability is maximized or minimized, I do not know what it is. Okay. So, if I do that, what I will end up with is I will end up with a critical radius that takes a form okay. So, that will be my critical radius. So, if I do that, I can recast my equation for delta A, and the equation for delta A then will become equal to 4 pi r square sigma times 1 minus 2/3 times r by r c, or I can write it in a non-dimensional form. I can write it as delta A divided by 4 pi r square sigma, or I divide it by 4 pi r c square on both sides, and so I will be left with r by r c whole square and then 1 minus 2/3 r by r c. Okay. So, if I plot this equation, so if I plot r by r c on one side, and if I plot my delta A by 4 pi r c squared sigma on the y axis, when my r is equal to 0, availability is 0, right, and when my r by r c is equal to 3 by 2, this term goes to 0, is not it. Okay. So, I know I start at 0 and at r by r c equal to 1.5 I go to 0. Okay. Let us see 1, 2, 3, 4, 5. So, this is 0.5, this is 1, no, hang on, I made a mistake, 1, 2, 3, 4. So, 0.3, 0.6, 0.9, let us say 1 is somewhere over here, right. Okay. So, and let us say this is 1 by 6, this is 1 by 3rd, and this is 2/3. So, let us say this is 1 by 3. Okay. So, if I substitute r by r c equal to 1, what do I get? if this is 1 by 3, right. So, if you do the plot, and I am not a very good person at drawing things, so I will make an attempt at it. Okay, so you will see it will go through a maxima at r star equal to r by r c is equal to 1 is where you get the maximum. Okay. And your value of delta A max is equal to then 1/3 times 4 pi r c square sigma, right. And but the big question is, what is R c? I still have not answered that question for you. Is it 1/3 or is it, yeah, it is 1/3 times 4 pi, yeah. So, now the question is, what is the value of R c? Okay, I know there is a critical radius. If I am below that critical radius, the vapor bubble will collapse, it will not be stable, and as long as my R is more than R c, my vapor bubble will survive. Okay. So, now if you look at this pool of liquid, let us say it is at a particular temperature, are all the molecules moving at the same speed? They are not, right. We will have a random distribution of molecules moving at different speeds, and if a certain cluster of these molecules come together and they have a speed which is above a critical speed, and the number of these molecules is above a critical number, then they assemble together and they call themselves a vapor bubble. Okay. But if that cluster of vapor molecules is less than R c, the size is less than R c, they might form a vapor bubble, but it will collapse, because the amount of availability that you create by the change in availability that you get because of the creation of that vapor bubble is less than that maximum, and so therefore, they will not survive. Does that make sense? Okay. So, now the question is, these molecules have to collide with each other, and there is a critical number of these ensemble of molecules that have to come together. So, number 1 is I need a probability of this collision frequency that exceeds a certain value, okay, and the number of molecules also need to exceed a certain number. Okay. So, one way to do that estimate is to use Boltzmann distribution. So, I do not have time to get into the derivation of Boltzmann distribution, but Boltzmann came up with this model where he could predict the collision frequency of molecules per unit volume. Okay. And that particular equation, this whole exercise I am doing is to figure out the value of that R c, which I do not know yet, right. So, what Boltzmann said was, if J is the number of clusters of molecules with a certain kinetic energy or velocity, okay, number of clusters per unit time, okay, per unit volume for a given system. Okay. And so, how do you define it? Well, he said that this J is equal to some frequency, a collision frequency f times e to the power of your activation energy, which is your delta max, divided by K, your Boltzmann constant, times the temperature of the liquid. Okay. And the distribution for F he gave was n times k times TL divided by H. So, n is the number of molecules per unit volume, k is the Boltzmann constant, H is the Planck's constant, and TL is the temperature of the liquid. Okay. So, then your J becomes equal to n k TL divided by H times e to the power of minus 4/3 pi R C square sigma divided by k T L. Okay. So, I can write down J H by n k T L. If I take the log of that, I will end up with minus 4/3 pi R C square sigma times 1 by k T L. And the second equation I have is minus my P G minus P L should be equal to 2 sigma by R C. Okay. I know the pressure of the liquid, I know the pressure of the system. I might be at 1 atmosphere, I might be at 10 atmosphere, I might be at 100 atmosphere. So, I have fixed the pressure of the liquid. Okay. And so, I keep varying the temperature, parametrically. I start at 100, then I go at 200, I go at 300, and so for each temperature TL I can calculate the value of R C. You all with me on this? Okay. If I know the value of R C, I know the value of P G. Okay. And the vapor bubble needs to be at the saturation temperature corresponding to that P G. Does that make sense? So, as long as the TL is the saturation temperature corresponding to P G, I have converged on my iteration. Okay. So, I keep varying it until I hit a P G where the saturation temperature corresponding to P G is the same as the TL. Does that make sense? Okay. So, I can do it in an Excel spreadsheet, or I can use a engineering equation solver or MATLAB, and I can keep iterating as long as I know the value of sigma as a function of temperature, because this sigma will vary with TL. Okay. Now, the big question is what is J and what is N? Okay. So, I can use ideal gas law to figure out the number of molecules per unit volume. Okay. K is a constant, H is a constant, J I do not know. I can have a cluster of molecules of 1,000,000 molecules, I can have a cluster which is 1000. Okay. So, J is a enigma, I do not know what the value of J is. Okay. So, let us go ahead and do this calculation for different values of J. Okay. So, I have summarized it in the PowerPoint. So, let us go ahead and look into it. Okay. So, these are the equations we already looked at. Delta G is maximum when R star is equal to 1. I apologize, for some reason the graphs are not appearing very well. And so, there are two equations, one is for R C, right, and then the other one is for the bubble pressure P B or P G. and the big enigma is I do not know what J is, but knowing the value of the pressure and temperature, I can calculate the value of density, and based on the density I can know the value of n. Okay. So, this I can find out for a given pressure and temperature, rest of them are constant. The surface tension sigma is a function of TL. So, if I fix TL, I fix sigma. Okay. So, I do the calculation, and so I did the calculations for, let us look at 1 bar pressure. Okay. And so, when my solution converged, when my J is 10 to the power 6 versus when my J is 10 to the power minus 6. Okay. What I find is my TL varies somewhere between 572 and 568 depending on the value of J I choose. So, my J went from 10 to the power 6 to 10 to the power minus 6, and the converged value of TL changed by only 4 degrees Celsius, which means my solution is not sensitive to J. I can assume any value of J, it does not matter, because I have taken a logarithmic, I have taken a log of J. So, therefore, it is not very sensitive. Even if I make a big error in the estimation of J, my answer will not change much. Does that make sense? Okay. And so, the converged value of RC comes to about 3.5 to 4 nanometers. Okay. And the pressure of the system comes out to about, the pressure of the bubble comes out to about 8 megapascals. Okay. Now, if I do that same calculation for 100 bars, okay, these are the numbers I end up with. The value of RC has not changed much, but what this tells you is you need very high values of temperature, very close to the critical temperature of water, in order for homogeneous nucleation to occur. So, it is very likely when you are heating up a liquid that you will ever reach homogeneous nucleation. Okay. So, homogeneous nucleation, if it ever occurs, usually occurs in a in a nuclear reactor, particularly for pressurized nuclear reactors. All right, because there you are operating very close to the critical temperature and pressure of your working fluid. Okay. So, now that I have guaranteed myself that homogeneous nucleation is not that much of an issue, and what that tells you is if I form a bubble which is of the order of 3 to 4 nanometers, the temperature and pressure of the system has to be pretty high. Okay, my temperature has to be pretty close to critical point, and the pressure has to be pretty close to the critical point as well. Okay. Keep that in mind. The next thing we are going to look at is heterogeneous nucleation. Okay. The bubble that forms on a heater surface. There you go. Okay, so let us go back to Clausius-Clapeyron equation. So, what your Clausius-Clapeyron equation tells you is how much does your saturation temperature change as the system pressure changes, right. So, your Clausius-Clapeyron equation is given by okay. So, HFG is your latent heat going from liquid to vapor or vapor to liquid, VFG is the change in specific volume. Right, and then T bar is your saturation temperature of the system. So, typically your liquid density is of the order of 1000, your vapor density is of the order of 1, right. So, so this in essence becomes equal to 1 by rho g, okay. VFG is basically 1 by rho g. Oops. So, I can write down my delta P by delta T as being equal to HFG divided by T sat times rho g. So, then your delta T is equal to delta P times T sat divided by rho g HFG. And what is my change in pressure? It is 2 sigma by R. So, this becomes 2 sigma by R times oops okay. So, what that tells you is the bubble that will nucleate on the surface of a heater depends on the temperature excess in the heater, okay. So, in other words, your delta T is equal to 2 sigma, well I already wrote it down. Now, how does the bubble nucleation occur on the heater surface? Okay. So, for that you need to consider how the heater was manufactured. Okay. So, for typical industrial heaters that are usually made out of copper, what they typically do is they cast the copper into blocks, right, and then they let the liquid copper solidify. So, if I look at the block of copper, when I pour the copper in and when I let it solidify, when it is solidifying, all the dissolved gases in that liquid copper, they start coming out. So, I end up with small bubbles that form, right. And let us say now I take it into a lathe machine and I cut it to shape, all right. So, the lathe machine comes in and cuts through. So, in the process, if I look at the surface now, my surface will look like this, and depending on the tool that I used in the lathe machine, I might also be making scratches. So, in other words, I get surface imperfections of different sizes. Okay. So, let us consider now we are in the tutorial phase of the lectures. So, let us consider a vapor bubble, I am sorry, not a vapor bubble, but let us consider a cavity. Let us say the cavity diameter is 20 microns. Okay, which means the radius of the cavity R is equal to 10 micrometer. Okay. So, in order for this cavity to nucleate a bubble, if I go back and use it in this equation, delta T is equal to 2 sigma by R okay. What is the value of delta T I will need so that a vapor bubble will nucleate over here? Okay. So, let us substitute. So, your typical sigma for water is about 59 times 10 to the power minus 3 newtons per meter times 2 I said the radius of the bubble is 10 micron, the cavity is 10 microns. So, that is 10 times 10 to the power minus 6 meters, right. I am at 1 atmosphere pressure. So, the water will boil at 373 Kelvin. Okay. The typical density of vapor is about 0.5 kilograms per meter cubed, that is my rho g, and the latent heat of water is 2.257 times 10 to the power 6 joules per kilogram, is not it. So, if I substitute all the numbers, anybody has a calculator? Any of you have calculator? I am sorry. So, this is 3.9 times what? Oh, I am sorry, yeah. So, what that tells you is if I have a 10 micron surface imperfection on my heater, I need at least 4 degrees Celsius superheat before a bubble will form. Okay. So, if I look at the nucleate boiling part of the curve, if I am plotting my q double prime as a function of delta t, right, I will need a delta t of about 4 Kelvin before my bubble will form, before my nucleate part boiling part of the curve will start. Does that make sense? So, as long as my heater temperature is less than 104 degrees Celsius, I will not nucleate a bubble. So, I am going to form a superheated liquid very close to the surface of the heater, but it will not nucleate a bubble. Okay. So, what happens? How does the heat transfer occur before the first bubble hits? Natural convection. Okay. So, I will be somewhere. So, I will be in the natural convection part here. This one will be my onset of nucleate boiling, and then I will have partial nucleate boiling at a higher superheat. Now, the question is how much is my heat transfer when I have natural convection? Okay. So, if I am in natural, if I am laminar flow, then it is C1 times delta T to the power of 1 by 4, right. And if it is turbulent, then it is some other constant C2 times delta T to the power of 1 by 3. So, Nusselt number is HL by K. Well, not really delta T. So, this is, let us call it C1. So, it is C1 times Rayleigh number to the power of 1/3, and this is, I am sorry, 1/4. Okay. So, let us substitute for Rayleigh number for the 1/3 case. I will have G beta L cubed times delta T divided by nu alpha to the power of 1/3. So, if I take this L cubed out, I will have H L by K is equal to C2 times G beta delta T divided by nu alpha to the power of 1/3 times L. And what do you see? The L cancels out. So, the heat transfer coefficient is independent of the size of the heater. So, as long as you have single phase flow, let us say you are in turbulent flow regime, the size of the heater does not matter, your heat transfer coefficient is sort of independent, but the moment two phase flow starts, now it becomes a function of L. We will see that a little later, but in any case, if you are in laminar flow, your H is some constant C1 prime times delta T to the power of 1 by 4, right, which means your heat flux Q double prime is H times delta T, and so that is C1 prime times delta T to the power of 5 by 4. You all with me on this? So, in laminar flow, your Q double prime is proportional to delta T to the power of 1.25, isn't it? Now, if I am in turbulent flow, my H is proportional to C2 prime times delta T to the power of 1/3, and so my Q double prime is proportional to delta T to the power of 4 by 3. So, if I round it off to the first decimal place, this is delta T to the power of 1 by 3, and this is delta T to the power of 1.3. So, whether you are in laminar flow regime or turbulent flow regime, your delta T is always proportional to the power of 1.3, isn't it? There is not really much of a difference in the heat transfer coefficient when it comes to natural convection, whether it is a laminar natural convection or turbulent natural convection. So, if I plot my log of heat flux as a function of delta T, I will get a straight line with a slope of approximately 1.3. Does that make sense? Okay. So, when I plot this graph, so if I am plot it on a log scale, this one will have a slope of 1.3, this one will have a slope of 3, because your Q double prime goes as delta T cubed. Does that make sense? Okay, you all with me on this? Okay, so what time is it right now? I'm sorry, 4:41. Let's stop here. We are running a little late. I wanted to finish some stuff today, but I'll do it tomorrow, and I'll speed up a little bit tomorrow. Okay, because officially we are supposed to stop at 4:30, isn't it?